great pleasure to introduce our first speaker, who you all familiar with, who's Smalyukh from University of Colorado, and he's going to tell us about liquid crystal defect photonics.
Thank you very much. So today, this is outline of my talk, and I'll discuss how we can use liquid crystal defects for photonic applications, different kinds of those applications. You can see that we will start from a discussion of how we can generate defects in the form of periodic lattices, and then later on how we can use them as diffraction gratings and also as generators of optical vortices. So by now, because we have a couple introductions, you're already familiar with optical vortices. You learned about them from Mark Dennis's talk, and also you are familiar how we can generate them using, for example, liquid crystal spatial light modulators, right? So in here, what we have is essentially defects in the phase of laser beams, and the particular example I'm showing in here is related to the so-called Gaussian beams, which are optical vortices. Now the question I want to ask is, can optical vortices control liquid crystal defects, and if so, can we then use them to generate periodic lattices of such defects and use them for different kinds of applications? So I'd like to start from giving you some background on how and why we can generate those defects, right? So we are all familiar with conventional applications of liquid crystals in displays and electro-optic devices, and we know how liquid crystal responds to electric field just to minimize the electric field term in the free energy, right? And so this brings me to my clicker question, which is related to a threshold voltage in a liquid crystal cell, just to check. And I guess I don't expect very large number of clicker votes so far. People are still coming. So we'll see who is on time using clickers. I'll stop system in 40 seconds or so. So in a liquid crystal cell device, this threshold voltage depends on, and those are possible answers. All right, I'll stop the system. Looks like we got some 25 volts so far. All right. So the correct answer indeed is E, B, and C. So it depends on elastic constant and the electric anisotropy. Good. So now how about if you have the same kind of a liquid crystal cell, but instead of applying low frequency electric field, we were to shine a beam of light into such a liquid crystal cell. So obviously in here we have pretty strong electric field at optical frequencies, right? And the intensity is proportional to square of that. We again will need to minimize a similar type of term in the free energy. And the difference is, however, that the dielectric anisotropy is that at optical frequencies, and therefore it can be expressed in this way in terms of the extraordinary and ordinary refractive indices. And so if you shine a laser beam of light into a liquid crystal cell, we'll therefore expect realignment at high intensities, right? And so again, to minimize this kind of a term in the free energy. However, if you were to then turn off the laser beam of light, we would expect director field going back to uniform undistorted state just to minimize elastic free energy, right? Because all of those distortions would cost some elastic free energy, and the system minimizes free energy to go to the ground state. Therefore, you can see that we would have to have the laser beam of light constantly present if we want to generate some interesting structures. And the question that naturally arises, would it be possible to somehow generate defects and other kinds of director configurations that would be stable over long periods of time, even after you turn off the laser beam that you're using to generate them? And so the answer is yes. During the rest of my talk, I'll discuss how we can do this, and then different types of potential applications that can arise from such defect and structure generation. So in this work, we will be using a cholesteric liquid crystal that has pitch comparable to the thickness of liquid crystal cell, and the cell boundary conditions are homeotropic, perpendicular, as depicted in here, so that the uniform cholesteric structure is totally incompatible with the boundary conditions, as you can see from this illustration. And then the system is in a frustrated state, right? Because the director structure would like to twist. It's a ground state, which is twisted because of the lack of mirror symmetry of the molecules that we use, that we have in this liquid crystal. However, at the same time, the boundary conditions are incompatible with this twisting nature of the liquid crystal medium. And so therefore, for this reason, we will completely unwind the cholesteric liquid crystal when we have the thickness of a pitch ratios close to unity. And therefore, we'll have uniform nematic-like state, although the system that we work with, this cholesteric liquid crystal, is chiral in nature. Now, however, if we shine a laser beam with vortices, as we discussed before, we can relieve that frustration and locally generate a twisted configuration. So the effect of shining a Laguerre Gaussian laser beam, as you can see, can be generation of a defect structure in here, twisted configuration that can be stable over long periods of time, even after we completely turn off the laser light that we use to generate. And so here is such a structure, you can see that it's fairly complicated looking with lots of colors. From a regular polarizing microscopy texture, it's a little bit difficult to tell what this structure might be. But now that I gave a previous lecture on different three-dimensional imaging techniques that one can use to visualize those complex three-dimensional director structures, you understand that we can actually probe it using those nonlinear optical imaging techniques in 3D and obtain images of this kind as I depicted here, right? And then from those images, reconstruct the director field configuration that would be a little bit difficult to guess based on such a polarizing microscopy texture alone as I depicted here. Now, so what we obtain in the process of such director field reconstruction is that what we have is essentially a double twist cylinder of director field that's looped on itself, right here in the middle of the structure, and then we have topological point defects above and below that looped double twist cylinder. So now you can see that far away from the configuration which we call Toron, the director is bending and can be uniformly can be embedded in a homeotropic texture in a liquid crystal cell, right? Because those distortions, band splay distortions around will decay with distance, and therefore we can embed it into a uniform liquid crystal cell. So now the question arises, why those type of structures are stable over a long period of time? Why is it that they can exist even after we turn off the laser beam? We can understand the physics behind in quite simple terms by simply looking at Frank-Osin expression for free energy. That's already very familiar for you after many tutorials we had. And so you know that in this expression we have different terms describing splay, twist, bend, and saddle splay distortions explicitly written here. And if we look at the two different configurations that we have, the uniform structure, which is frustrated, cholesteric, where the boundary conditions prevent the director field from twisting, and this structure with a lot of twists, the double twist cylinder, but also topological defects, we understand that the different terms in this expression compete with each other, right? So for the twisted configuration, obviously twist and saddle splay terms are minimized, while for the uniform structure, the splay and bend terms are minimized because there are no splay and bend distortions. In the case of this Toron configuration, in addition to twist, which is favorable, the liquid crystal would like to have twisted configurations over distances comparable to cholesteric pitch, right? But in addition to those distortions, we also have topological defects and band splay distortions, right? And so therefore, because of competition between those all different terms that all want to be minimized, we can have two local minima. One corresponding to the uniform director configuration here, and the second one corresponding to the Toron configuration depicted in here. Now, there is, however, a very strong energy barrier to go from one configuration to the other. Strong, I mean, it's comparable to thousands of K Boltzmann T, so that the system cannot go from one state to the other state on its own. However, we can use laser beams like Gaussian beam I discussed before, or other types of beams, or we could use voltage to initiate transitions from one configuration to the other configuration. So with the laser light, we can go back and forth between uniform and distorted structure. With applying voltage, we can only go in the opposite direction. And so, again, the reason why both of the configurations can be stable is that there is this competition between different terms in free energy. What I discussed, this very simple picture of stability of the Toron configurations, can be also understood by means of numerical modeling, by numerically minimizing this expression of Frank-Osin free energy, and then plotting the total free energy density isosurfaces, as shown in here, and the different colors simply depict the changes in local free energy density. And so what you can notice by looking at this structure is that in the middle part of the cell we have low free energy region, because this is the place where we have the double twist cylinder, and both twist and saddle splay terms are minimized in here. However, the regions of point defects and vicinity of those point defects are quite energetically costly, as you can see from this color scale, and therefore the overall free energy of such a structure can be comparable, can be lower or slightly higher, but definitely a metastable state, and in many cases also stable state in such confined cholesteric liquid crystal cells. So now what would happen if instead of just Gaussian beam we were to shine of Lagrange Gaussian beams of different charge. So what would happen if we were to change the topological charge of those beams? So in here you can see a structure that's generated, shown in this polarizing microscopy texture, generated using a beam with charge 9. Then if we switch it to topological charge 5, we can see the structure change somewhat. And then if we further change it to 3, the configuration of director field changes as well, as evidenced by the polarizing microscopy textures. And so now by means of three-dimensional optical imaging, we can follow those changes that are observable in polarizing microscopy and see that they also correspond to changes of topological defects. For example, you can go from point defects to loop defects and back, and the summary of defect structures that we can obtain by playing with different charges of Lagrange Gaussian beams is shown here on this slide. So in all cases we have double twist cylinders looped on themselves, a configuration shown in here, and then in addition to that we can have point defects or disclination loops as shown in here, and those topological defects allow us to match the boundary, the director structure in the double twist cylinder to the far field director, right, while also somewhat minimizing overall free energy. And so in here you can see 3 different types of structures where we can have point defects, we can have point defects and loops, or we can have loops on opposite sides from the double twist cylinder. Now, it is also possible to have structures without such point defects, but this will not be a subject of this particular discussion I have today. What this shows us is that we can use the defects in the laser beams of light to control topological defects in liquid crystals, right? Because all of those different structures you can see in here could have been obtained and controlled by simply controlling the different optical vortices that we use to generate and manipulate them. Now, many different varieties of structures similar to the ones I showed you can be generated. A really zoo of different structures, and in here I just show some examples of them, right? So you can see that they have some features in common, but there are also noticeable differences between them, and so we can probe using the three-dimensional imaging and study the details corresponding to those structures. But before I discuss some of the examples, not all because of lack of time, will not be able to go through many of them. I just want to mention that they are quite analogous to many other interesting condensed matter systems. You might have heard about Skyrmions, braided Skyrmions, Merons, Bimerons, and so on, and those kind of topologically interesting configurations are being realized in, say, chiral ferromagnets and Bose-Einstein condensates and so on and so on. But we can see that they can also be generated in liquid crystals using optical vortices. And so in here you can see the Skyrmion structures as an example that are topologically interesting because they are similar to topological defects, and although the variation of vector field in this case in the texture is smooth, yet they are topologically distinct from uniform state, similar to that of, say, point defects in ferromagnetic systems. Now, here's another example of Bimerons, and you will see that in the case of liquid crystal defects in cholesteric confined cells, we can obtain analogs of such defects in ferromagnetic systems, for example. And so it's important to remind ourselves the different types of defects that can occur in cholesteric liquid crystals, because this twisted nature of cholesterics really increases diversity of defects that we can have. Obviously, topologically, they may be similar, right, as you remember from Randy Kamyan's tutorial lecture, but in terms of energetics, there could be big differences, right, because the defects that would have singular cores would be much more energetically costly, like the defects in here, as compared to the defects that have non-singular configurations. And so in here I just show very briefly the different types of defects one can have. The so-called lambda disclinations, where the director is along the actual defect line, so it's non-singular in the material director field, and this is twist escaped director configuration essentially. Now we can also have another lambda minus 1 version of opposite sign compared to this one. We can also have twist disclinations. We can have lambda tau and also chi disclinations, which are different in terms of energetics of those defects. So one type of structure that's different from the Toron that we can generate is the baby Skyrmion configuration that you can see depicted in here, right? And so you see that the basic structure in here is a double twist cylinder perpendicular to the flat substrates of the liquid crystal cell, unlike in the case of Toron, where we had a double twist cylinder looped on itself, right? And so this double twist cylinder is now matched to perpendicular boundary conditions by two disclination loops at the top and at the bottom. In the middle of the liquid crystal cell, however, we can see that the configuration is looking somewhat similar to what we observed before in the Toron case. Now, in the case of this baby Skyrmion configuration, you can see that the director of the double twist cylinder is matched to perpendicular boundary conditions by means of loops of two disclinations, twist disclinations, and the structure of those is depicted in here. All right, and so this slide shows you some details of the configuration of director field as the director of the double twist cylinder inside of the baby Skyrmion is matched to the perpendicular boundary conditions at the substrate. Now, I will not be able to discuss many of the other configurations that occur in here, but just one example to show you diversity of those configurations, right? All of them have something in common. There are some combinations of director twist, right, and topological defects. And then because we have so many different types of topological defects that can occur and different types of twisting behavior that can occur, we really have a diverse a large number of structures that can be observed. And so here you can see in-plane and vertical cross-sections of another configuration that can be obtained. Now you can see there is much more twist as you would go from the central part of the vertical cross-section of director configuration to the periphery. So instead of just twisting by pi, we have twisting by 2 pi in all radial directions in here. And the structure is also asymmetric with respect to the middle plane of the liquid crystal cell. Right? So on one side we have so-called lambda disclinations, loops of lambda disclinations. On the other side we have twist disclination loops, this makes the structure, as I already mentioned, asymmetric with respect to the middle plane of the liquid crystal cell. Now we can control what kinds of structures occur by means of using different optical vortices, and also using different types of boundary conditions, strong anchoring, weak anchoring, and so on. And all of those configurations and many more can be obtained in those confined cholesteric liquid crystals. Now, one can generate Torons in other localized configurations in two different forms. One is in such a way that they behave like Brownian particles, simply undergoing two-dimensional Brownian motion in the liquid crystal cell. And then they even interact with each other like quasi-particles, right? So if you were to bring two such particles, two such quasi-particles, Torons, close to each other, let them interact, you would see them repelling from each other, and the distance between the centers would be gradually increasing, as you can see depicted in here, distance versus time. Now, however, if you were to just slightly increase the generating laser power a little bit further, you can generate those structures in the locations of interest while avoiding Brownian motion at all. So those Torons would be then pinned in exact locations of interest for us, right? And so you can see in here that this periodic structure with a channel, bifurcating channel in here, was generated simply by using somewhat higher laser power, and higher I mean by 20% or so, which allows us to pin the generated Torons in the locations of interest. Now, if we use slightly lower power, or at the periphery, the power was slightly lower, then you can see those Torons are walking away from the locations where they were generated, right? And so now we can combine the diversity of configurations that we had before, right? We could obtain twisted configurations with all kinds of defects by using different optical vortices and boundary conditions, now we see that we can pin those configurations in desired locations. And if we combine those two notions, we can then, for example, form CU letters, standing for Colorado University, not Cambridge University, in those locations of interest, right? Now, what other things we can generate? Well, here are some examples. You can see honeycomb lattice of Torons. In here, you can see a quasicrystal-like looking configuration which we built by simply using a Nature article depicting colloids in such a configuration, which we simply copied and replaced by Torons in our liquid crystal cell, right? And so just to point out that in all of those locations, the little points that you can observe there are nothing else but fairly sophisticated configurations of Torons with double three-cylinder and two-point defects on the opposite sides. Now, looking at those configurations, which are fairly periodic, you probably realize that they could be potentially useful, right? For example, as diffraction gratings. And so indeed, if we were to shine, say, a helium-neon laser beam through such a periodic pattern of Torons, we would realize that we get a pretty high-quality diffraction pattern. And so here, those two patterns have been obtained for exactly those two different diffraction gratings of Torons. You can see that the quality of pattern is pretty good. Moreover, we can control the intensities of laser light in different orders by simply applying voltage. And in here you can see that by tuning voltage in the range from 0 to 5 volts or so, we can change the size of the Torons, and therefore the contrast of refractive index in this periodic lattice, and with that we can tune intensities of different diffraction orders in the beams. So here it's how this can actually happen, right? So this is another example hexagonal periodic lattice, and we are applying voltages which are depicted in the bottom corners of those images. And you can see that the contrast changes, and those are just regular polarized and microscopy images. And the size of those Torons changes a little bit too, until we fully erase them at 2 volts or so, right? So this is now purely homotropic texture. And this nice periodic array that we had was fully erased. Now the corresponding diffraction patterns at different applied voltages are shown in the top corners of the images on this slide. And so you can see that we can control diffraction patterns by simply applying fairly low voltages to those diffraction gradients. So now we come to our next clicker question. And the system is on, so please start working. So it's a question about dislocations. Right? We had tutorials. None of the tutorials was specifically focused on dislocations, but those defects have been mentioned a couple of times, I think at least, during the summer school, and I hope you heard about them before. Yeah.
That previous slide, that was a DC voltage applied through the
AC,
cell.
1 kilohertz. All right, I'll need to stop the system. So only 41 volts so far. So many people are sleeping still. Okay, I'll stop the system. So let's see what we got. Most popular answer was A. Then E was a little bit popular. D was somewhat popular. So A is the correct answer. Indeed, those are defects both that can be observed in crystals and certain types of liquid crystals, right? So let me see. And actually, not only in crystals, liquid crystals, but many other periodic media. And here you can see a dislocation that we deliberately introduced into a periodic lattice of Torons. And so now we have Torons which are themselves formed by defects, right? You remember there are point defects in each of those little Torons here, 2 of them at the opposite glass plates of the liquid crystal cell. And then we also introduced a defect in the periodic lattice that we generated. So we have hierarchical structures of defects here. But then if we shine the same helium-neon laser beam through this configuration, in the diffraction pattern, unlike in the previous cases of nice periodic arrays without defects, we now see that the first order diffraction beams in here have little black dots, dark dots in the middle, right? And so each of them, and this tells us that those might be optical vortices as well, because as you remember from the discussion of Focused Gaussian beams that I overviewed, and you learned also about previously during the tutorials we had during the summer school, when we have an optical vortex, because of phase singularity or undefined phase in the middle of the beam, the intensity will go to 0, right? And so now we can probe the phase corresponding to such diffracted laser beams, and here you can see the phase plotted in a three-dimensional plot and visualized also using colors. And so indeed we have nothing else but screw dislocation in the phase of light. And as we would go to the beams of higher orders, we can have screw dislocations of larger Burgers vectors. So in a sense, here you can see on this slide the dislocations in the periodic lattice, the edge dislocations, and also screw dislocations in the phase of light. And the phase profiles that I just showed have been measured using this Stokes polarimetry setup that is depicted in here, where we again use a laser source of light that's split into two different beams, and then one of them is sent through the liquid crystal sample with Torons forming a periodic array and a dislocation defect in it, and then recombined. Eventually we probe in here the phase profile by rotating the quarter-wave plate and the polarizer and measuring the intensity distribution using the CCD camera. From the data of intensity measured for different orientations of the quarter-wave plate and polarizer, we can then obtain the Stokes parameters S2 and S3 using those simple expressions, and then from those one can calculate the phase profile as a function of coordinates. Right, so in here are some more examples of defects in the periodic lattice of the Torons, the hexagonal in this case, and you can see 5-7 defect pair here in the very center of it. We can obtain a diffraction pattern, characterize the phase profiles corresponding to those laser beams that are in different diffraction orders, and then those can be compared to the computer simulations, and we can see good qualitative agreement in terms of the types of defects that we have in those diffraction patterns that are generated by defects in the liquid crystal samples. And again, this is to remind you that each of those little dots in there was a Toron, a combination of defects separated by a double twist cylinder. Now, if we were to, instead of scanning the laser beam between different locations in the liquid crystal sample, if we were to drag the laser beam inside the liquid crystal, we can generate linear configurations. And in here, by looking at this image, you can notice that we can also generate those linear configurations of different types. In this location, this is a finger of the first kind, which is pretty much built by a quadruple of the so-called lambda disclinations that I showed you before, of opposite signs. And the slightly different structure that you can notice in here is a cholesteric finger of the second kind, where we have +1 disclination in the middle and two -1 over 2 disclinations at the periphery, top and bottom substrates of the liquid crystal cell. Now we can generate those configurations and then compare, the model, which is this model of director field is obtained again by minimizing Frank-Ozin elastic free energy, and indeed for both types of fingers of the first and second type, both polarizer microscopy textures, the experimental and simulated ones, and also the 3-photon self-fluorescence textures, experimental and simulated ones for the two different types of structures are in a very good agreement with each other. Right, so now in addition to generating rings and spirals of different kinds, we can again generate diffraction gratings, as you see depicted in here, the corresponding diffraction pattern. We can also generate more interesting configurations like this cat from the book that mathematicians quite often use. Right? We can reproduce it in a liquid crystal using defects. I don't know if this would have some photonic applications, but could be interesting to ask a question like that. And so you can see that those type of defects are formed by quadruples of lambda disclinations, and the reason those defects in the quadruples do not annihilate with each other is just because they are separated by cholesteric twist, and because the liquid crystal is of cholesteric type, the twisted configurations are favorable and they stabilize the defects that we obtain in here. Alright, so now we again can produce hierarchical structures. So in here is a grating that forms a dislocation in the middle, and here an additional inserted layer. And again, if we diffract helium-neon laser light through such a configuration, we can see that again the higher order diffraction beams have little spots in the central part, and those spots are different depending on the Burgers vector of the dislocation in the grating that we introduced. By probing the corresponding phase singularities and phase profiles, we can establish the relation between the Burgers vector of the dislocation in the diffraction grating and that in the diffracted beam of light in the given order of the diffracted beam, right? And so you can see that, for example, when we use elementary dislocation with Burgers vector being equal to one inserted finger in here, in the first order we have just one spot, and here we have two. So this is higher Burgers vector or higher charge optical vortex as compared to the one in here, right? And so this is a simple relation that we have that relates the number of spots that we have and the diffraction order that we deal with, and this is Burgers vector and the periodicity of the fingers that we have in the grating. So now, however, what's interesting is that the high charge optical vortices tend to split into lower charge optical vortices, which probably reminds you of the splitting of high strength defects in liquid crystals that we are familiar with into lower strength defects, right, just to minimize free energy. And here, similar thing happens, but for a different reason. So we do not have energetics reasons for splitting those high strength defects, but this is just due to the presence of weak coherent background and screw dislocated waves that drives this behavior. So now I will just quickly show you a couple other examples that we can have. So other types of defects can be generated, and this kind of pair of defects, for example, can be used to generate twisting vortices induced by those defects in the grating, and the theoretical prediction predicts dependence of this kind of the angle of the twisting between the optical vortices as a function of distance from diffraction grating, and indeed we observe this in experiments. Another type of defects, and in this case this allows us to generate interlinked screw dislocations in optical vortices, and you can see the phase profile corresponding to them in here. So not only we can obtain those patterns of fingers with dislocations, but also we can control them by applying external field, just like in the case of Torons, and that allows us to control the diffraction patterns. Now, what's interesting also is that we can generate those Torons in the regime where they behave like Brownian particles or quasi-particles, right? And then they start interacting with each other and also interacting with fingers. And then here you can see some examples of self-assembled configurations of Torons and fingers that we can observe. And my question to you is, why do those interactions occur? What drives the self-assembly? In this case, between, I'll give you half a minute. And then because we are running out of time, I'll probably skip 2 remaining slides that I still have. And we'll go to conclusions. Okay. There are many more people, even the ones who voted for the previous question. So don't be shy. Okay, I'll stop the system in just a second. Okay, so B was most popular answer, and this is indeed correct. So I'm very happy the way you answered it is indeed very good. So I'll skip those slides which are describing 3-dimensional configurations of Torons and fingers. I'll bring to conclusions I will leave them on that conclusion, the conclusion slide with you, but before I do that, I want to acknowledge students in my group, and in particular Paul Ackerman, who is here with us today, also Rahul Trivedi, and others who contributed to this work. All right, so thank you for your attention.
So we're running a bit late, so a couple of quick questions.
You have shown that a regular pattern can be used as a diffraction grating. Which type of diffraction grating you are thinking? Is this phase diffraction grating or amplitude diffraction grating?
It's phase diffraction grating, and it's working in Raman-Nernst regime, right? Because the periodicity in the structures I showed you were larger than wavelengths of light used to diffract, or the diffracted beam. We can also go to the other regime, to the Bragg diffraction regime, but not in this case.
So when you applied voltage, it was a DC or AC?
AC, 1 kilohertz, just like what you use in this place.
But intensity of the secondary diffraction ratings are just decreasing. Why? But if you are
because you are changing the contrast between different locations in the grating, right? So you have a director configuration and refractive index, as we again saw from tutorials during the summer school, is dependent on direction of light propagation, right, compared to director field. So it will see the refractive index contrast, and that contrast is up to delta n of the material. Right?
Any other questions?
Why your defects go Brownian motion?
Pardon?
Why your defects move in Brownian motion? I would expect.
Well, it's thermal fluctuations. I mean, it's just like with the particles for very similar reasons with Brownian colloidal particles.
But they also have elastic interaction with other Torons.
Yes, they do interact, and it's just like if you were to have other colloidal particles, they can interact and all undergo Brownian motion.
Any other questions? I have a question.
Yeah.
Which is, you said that these things last forever. I mean, Torons. Did you ever try to really measure the lifetime of one of these?
Well, very old samples which are like 3 years old, they still can contain the lattices and so on, but we didn't make a specific effort on testing. And then this is fairly new stuff, so we cannot tell about 10 decades or something like that. Maybe we'll store some samples for future generations.
Okay. So thank you, man, again for a lovely talk.